The year is 1971. The Cold War, while still 2 decades from its end, was clearly not going well for the Soviet Union. They had lost the space race. The wealth gap between social classes continued to grow. A desire to industrialize resulted in more food shortages. And the people were always looking to the West, where they saw endless prosperity. All of this should have been welcome news to the United States. Their prime competitor on the world stage was falling behind, both in economy and military capability. Its population was slowly turning against their leadership. But that increasingly desperate leadership had something the United States feared: one of the largest stockpiles of nuclear weapons in the world, with many pointed directly at the land of the free. If that leadership was pushed into a corner and saw no other way out, those WMDs may find their way into the West in a very unfriendly manner. While many of said nukes could be launched directly from the land, the scariest among them were those carried by ballistic missile submarines, whose mobile nature allowed a nuclear strike from anywhere in the water. What the United States needed, more than almost anything else, was to know when and where these apocalypse machines were being sent at any given time. Somehow, they needed to listen in on the Soviets to get the information they so desperately desired. Enter Operation Ivy Bells, an American espionage mission jointly operated by the CIA and NSA with the task of doing just that. So secret was Ivy Bells that its top-secret classified mission had a top-secret classified cover story. It went that the mission was to recover parts of Soviet anti-ship missiles launched into the sea, and most of the crew believed this to be their only directive. Only a select few knew the true nature of their presence deep within Soviet-held waters, installing a listening device onto underwater communication cables to hear exactly what those elusive ballistic missile subs were up to. Just one thing: those communication cables sat in 400 feet of water, and the listening devices had to be put in place by divers, and not those of the breath-holding variety. Not only that, but these divers would need to remain underwater for hours at a time, and would not return to 1 atmosphere's worth of pressure for much longer than that. Clearly, Ivy Bells has some explaining to do. Those questions and more will be answered here today on the 3rd installment of Full Ocean Depth. This is episode 3 of a 5-part series examining how humans gained the knowledge and technology that allowed us to descend to the bottom of the ocean. Last time we took a look at diving bells and compressed gas, and today's installment we'll look at Ivy Bells and boutique gas. YouTube tells me most of the people watching my videos aren't subscribed, so if you're interested in these topics or those related, please consider subscribing, as more is sure to come in the near future. With that out of the way, let's get into it. To understand how Ivy Bells ever became more than just a pipe dream, we first must understand the scientific hurdles overcome since the time when divers only used compressed gas. In the last installment, we learned about nitrogen narcosis and how it affects us at various depths. We also discovered that after breathing air at higher pressures, our bodies needed time to ascend to shallower depths, so as not to get the bends. At roughly 100 feet, the nitrogen absorbed into the blood makes us feel somewhat buzzed and unfocused. However, by the time we reached 250 feet, that euphoric sensation turned from a dream into the worst nightmare imaginable. The problem has a relatively easy solution, however. If we breathe gases with a lower concentration of nitrogen, that should hypothetically allow us to dive deeper without experiencing the effects of narcosis. This hypothesis is exactly correct, and is the philosophy behind Nitrox, the most common form of boutique gas, meaning any safely breathable gas mixture that is not the same as our atmosphere's chemical makeup. Nitrox is essentially standard air, but with a lower percent of nitrogen in it, replaced instead with more oxygen. It comes in a range of forms, the most common being EAN32 and EAN36, meaning 32% oxygen and 36% oxygen respectively, compared to our atmosphere's 20.9% oxygen. This mixture has a couple benefits. First, as previously stated, it allows us to dive deeper without experiencing the effects of nitrogen narcosis. Second, it allows us to stay at depth for longer periods of time without needing to spend lengthy periods of time in the shallows to decompress. However, it does have a drawback, and it's kinda a big one. Everything has what's known as an LD50, and it means that half of all test subjects would be dead if given the LD50 of any given substance. Essentially, everything is toxic, no matter what it is. Sure, there are things that are toxic even in very small doses, like bleach or cyanide, but what about stuff like water, or in our case, oxygen? By increasing the concentration of oxygen in our boutique gas and diving down with it, we have caused the depth at which we reach oxygen's LD50 to become shallower, a point in which our bodies experience something known as acute oxygen toxicity. How much shallower, I hear you asking? Well, fortunately, we can calculate it using this equation right here. Let's do an example. By plugging in 32% oxygen, that's one of the most common nitrox mixes, we can see that our maximum safe depth is 132 feet. But it's a far cry from the 250 we managed last time, and nowhere near the 400 feet achieved by the divers of Ivy Bells. So what do? Nitrogen limits our safe diving depth, oxygen limits our safe diving depth. How are we supposed to get deeper? Fortunately, there are gases other than nitrogen and oxygen. Let me introduce you to our savior, helium. It sits in this peculiar location on the periodic table, but that's because it's a noble gas. The lightest one, in fact. And because it's a noble gas, it has its outermost valence shell full. That meaning full of electrons, meaning it's inert and won't readily bond with other elements. That's great. Shouldn't have any bad side effects on our bodies. Well, nothing is perfect, but it is unequivocally better than nitrogen. Oxygen and helium mixtures is what deepwater divers breathe, and it goes by the name Heliox. Let's pull up that equation again. Common Heliox mixtures include 90% helium and 10% oxygen on the low end. Not a ton of oxygen to go around, but as long as you're not trying to run a triathlon, you should be okay. Plug in the numbers, and we get a maximum depth of an incredible 495 feet. Divers on very small percentages of oxygen have made dives to beyond 2,000 feet. That smashes our current record for both free diving and compressed air. Now you may be wondering, why don't all divers breathe Heliox? Well, for one thing, helium is expensive. It may be one of the most common elements in the universe, but that isn't the case on Earth's surface. The equipment needed to dive on Heliox is expensive too, and diving equipment is already expensive enough. That's why it's often reserved for industrial applications such as underwater welders working on oil rigs or the operators on our enigmatic Ivy Bells. Also, you may not want to go quite so deep for extended periods of time breathing this stuff in, because while it aids us in preventing the effects of nitrogen narcosis, it does not stop us from lengthy decompression times. That's what the increased oxygen concentration was for. And if you go diving to 495 feet on a scuba tank of Heliox, with no way to have air pumped to you from the surface, you may not have enough in the tank to make a safety stop, or even a safe ascent to the surface. So you may be wondering, how are underwater welders and Ivy Bells staying at depth for so long? The answer? Saturation diving. When you ascend after a fairly deep dive, you need to make a safety stop. We've been over this. Helium builds up in your system, and you need to let it off gas as you ascend slowly. The longer you're at depth, the more saturated your body becomes with helium, and the longer your safety stop needs to be. But at some point, your body is fully saturated by helium. Let me explain. If you pour salt into a glass of water and stir, it dissolves. Big whoop, we all knew that. But if you pour enough, it stops dissolving. This is because the water is fully saturated with salt and can't hold any more. The same thing happens with your blood. After breathing Heliox for a certain amount of time, your blood will get fully saturated with helium, and no matter how much longer you stay at depth, your decompression time will not get any longer. This opens up opportunities. Deep depths are not required to experience high pressures, as we have seen with decompression chambers. People can breathe compressed gas, or in our case Heliox, in these chambers while doing various regular people things. So when an underwater welder is commissioned to do a job, instead of returning to the surface after each dive and dealing with decompression times that would take longer than their time at depth, they stay in something known as a hyperbaric chamber. Essentially, they are living underwater. And when the job's done and it's time to come back up, the hyperbaric chamber is raised over the course of several days, the pressure inside decreasing slowly over that period to allow the divers to decompress. And when they step out of the chamber and breathe in regular air, the helium in their blood is able to safely off-gas itself, because there is no longer any pressure difference between the inside and outside of the hyperbaric chamber. And it is with this technology that Ivy Bells was able to succeed. Those operators worked out of a hyperbaric chamber similar to underwater welders, installing listening devices undetected by the Soviets while effectively living under constant pressure, both literally and figuratively, by an adversarial nation and environment alike. But even after all we have learned, Ivy Bells is still missing pieces necessary to complete its mission. That hyperbaric chamber and divers didn't just appear in Soviet waters one day, they were transported there by a seaworthy vessel. It couldn't have been a surface ship. They would have been detected easily. Ivy Bells succeeded, not just due to advancements in boutique gases and saturation diving, but another technology, one very different from what we have discussed so far. But that will have to wait until next time. Thank you all so much for watching. The previous episodes discussed topics I was already mostly proficient in, but chemistry has always been somewhat of a weak point for me. Fortunately, this episode wasn't too chemistry heavy, and I think I explained it well enough for anyone to understand with relative ease, provided you've seen the other episodes. There was a lot of science that needed to be explained here, so I wasn't able to make a ton of room for jokes. I hope it was at least tolerable though. Anyway, that's all I got for today. You all have yourselves a good one, and I hope you learned something.